Hey guys, it's Margot at Lanterna here. I'm a maths tutor for Lanterna and I'm really excited to be bringing you a number of maths videos specifically for the applications and interpretations IB maths syllabus. So in these videos, we're going to be picking out parts of the syllabus which I found students find a little bit more tricky sometimes. And we're going to be starting off with matrix algebra. So we're going to do this in two parts. This is part one. The reason I've decided to start here is because this is an entirely new addition to the IB maths syllabus, specifically to applications and interpretation. So matrix algebra hasn't been seen anywhere on the previous maths syllabi before. So I thought this would be a great starting point. Here we're going to be covering the first part of section 1.14 of the higher level syllabus. So looking specifically at the definition of matrices and then matrix operations. So really the fundamental basis of matrix algebra. So I hope you find this video useful, guys, and I hope you enjoy it. So first of all then, the definition of a matrix. What is a matrix? Well, a matrix is a rectangular array of entries or elements, or they could be numbers or they could be symbols, for example. And we refer to the size of a matrix as the order of a matrix. And we denote this order as m times n, where m is the number of rows and n is the number of columns. And we call each number or symbol in this matrix. So for example, if we were to look at just that number, we would call this an element or an entry of a matrix, and we denote it as a subscript ij, while I denotes the row number and j the column number. Good. So starting to look at some matrix operations then. First of all, equality. Two matrices can only be equal if they have the same size. If they don't have the same size or order, as I mentioned in the previous size, there is no universe in which these two matrices can be equal. So that's your first thing to check if you're looking at the equality of two matrices. Then second of all, the condition under which two matrices are equal are if the corresponding elements are equal. And what do I mean by that? Well, say we have a matrix 4, 2, 1, 6. So it's order 2 times 2. It's a square matrix. And we have another matrix 4x, x squared minus 3. And 6, and we want to check whether these two matrices are equal and under what conditions they're equal. So let me just call this matrix first of all A, and let me call this matrix B. So we said two matrices are equal if their corresponding elements are equal. And what do I mean by that? Well, we mean that the entry of the first row, first column of A is the same as the entry in the first row, first column of B. In this case, we see that is correct, right? Also, we mean that the first row, second column of A must be equal to the entry in the first row, second column of B. So in this case, the condition under which that is true is if X is equal to 2. Well, let's check that this matrix can be equal by comparing this entry in the second row, first column of A and of B. We see that in order for these to be equal, we have that x squared minus 3 must be equal to 1, therefore x squared must be equal to 4, and we find that again, for this to be equal, x is 2. So we see therefore that these matrices are equal if x takes the value 2. Moving on then to addition and subtraction. So say we have a matrix C, and it's equal to the sum of two matrices A and B. Again, we have a condition that we need to comply with if these matrices are to be equal, and that is that, again, to add two matrices, they must have the same size. So A and B must have the same size, and then C is going to have the same size as both matrix A and B. And now to find the entries or the elements in C, what we have to do is we have to add the corresponding elements of matrix A and B. So let's take an example. If we have 1, 2, minus 3, and 4, and we want to add that matrix to another matrix, 0, minus 4, 6, and minus 3. Then we have to add each entry. So we look at, for example, the first row, first column. We have to add it to the first row, first column of our second matrix. So that entry of C, first row, first column, is going to be 1 plus 0. Now, first row, second column entry of matrix C is going to be first row, second column of A plus first row, second column of B. So that is 2 plus minus 4. Similarly, if we do that with the other elements, we see that we have minus 3 plus 6 here, and we have 4 minus 3 over here. So overall, our matrix will equal 1 minus 2, 3, and 1. So that is addition, and the same would go for subtraction. Next then, multiplication by a scalar. So unlike the two cases we just looked at, we can always multiply any matrix by a scalar, and all we have to do is we just multiply each element by that scalar. So for example, if I had a matrix 1, 4, 3, and 7, say we wanted to multiply this matrix by 2, then all we have to do is multiply each element by 2. So we have in the first row, first column, 1 times 2, which is going to be 2. First row, second column, 4 times 2, which is going to be 8. Then over here, we're going to have 6, and finally 14. So that is multiplication by a scalar. It's pretty simple. Finally then, this is where it gets a little bit more tricky. Matrix multiplication. Say we have a matrix C and it's equal to the product A times B. Now again, we have a condition under which the matrices A and B must hold in order for them to be multiplied together. And that is the number of columns of A must equal the number of rows of B in order for these matrices to be multiplied. So what will our matrix C then look like? What will its size be? Well, the number of rows of matrix C is going to be the same as the number of rows in matrix A, and the number of columns of C is going to be the same as the number of columns of matrix B. So just to summarize that information, that's maybe a little bit kind of, tricky to remember, because a lot of rows of that is equal to columns of that, and rows of that is equal to columns of that. It's quite simple I always found it very useful to kind of remember this using this little diagram. So if we have a matrix A and we have a matrix B, then what I do is I'd write down the order of each of these matrices like this. So say we have, these general orders. To check that we can actually multiply these matrices, well, we have to compare these two, right? We have to compare the number of columns of A and the number of rows of B. And if these two are equal, we can multiply our two matrices. So that is our first check. If these two are equal, we can multiply them. Okay, and then we said that the order or the size of C is going to be the number of rows of A and the number of columns of B. So this here, our order is going to be M cross P. That's a way that I found it useful to just, first of all, check whether I can multiply them, and second of all, see straight away what is the size of my product going to be. Okay, well, once we've done all of that, how do we actually find the elements of the product, or the elements of our matrix C? Well, to do that, we have to multiply the ith row of A by the jth column of B. So we see here we have the ith row of A. Remember, Aij, I is the row number and J is the column number. We have here the ith row, and here we have the jth column of B. And what we do is we multiply the corresponding elements. So we take this first element and multiply it by the top element of B. And we have to add that to the second entry. So AI2 times B times 2J. So one way to imagine this essentially is, imagine if we were to flip this matrix A right here. What I mean by that is just imagine writing it as, or visualize it, AI1, AI2, ... and then AIN. And then what we see, we just have to multiply the top components and then the second components and every corresponding component and add them together. So you need sort of imagine you're trying to rotate that first matrix, and that kind of makes it a little bit easier to see. Okay, so let's just look at a little example of this. Let's look at a simple example. We're going to have a look at a matrix A, which is 1, 2, and minus 1, and a matrix B, which is going to be 3, 4, and 2. Right, so we see that this first matrix here, A, has an order, well, it's got 1 row and 3 columns. We've got 1 times 3, and the second matrix here has 3 rows and 1 column. So we see here, right, well, we check first of all, these two numbers are equal, hence we can multiply them, and then this is going to be our order of our product. So we're just going to have a matrix which has 1 entry as this product. Okay, so let's work out that 1 entry then. Well, we said, remember, that we have to multiply this first component of the ith row of A, so the first row of A, by the first component of the jth column of B. So we have 1 times 3, and remember we have to sum all of these corresponding components. So we have 2, which we multiply by 4, so 2 times 4, plus the last one is going to be that third component of the ith row times the third component of the jth column, minus 1 times 2. So overall our 1 entry is going to be 1 times 3 plus 8 minus 2, so that's going to be 9. So that is our answer to multiplying these two together. Now let's look at a slightly trickier example. Okay, so we're going to have a look at this problem right here. So again, we're going to just do that check that we can multiply them and find the order of our product. Well, this matrix here, we have 3 rows and 2 columns, and here we have 2 columns and 3 rows. So here we check these two are equal. Great, we can multiply them. And then we see from these two outside numbers here what the order of our product is going to be. So in this case, the product is going to have order 3 by 3. So let's work out this product then. Well, how did we do that? Okay, well, we had to multiply the ith row of A by the jth column of B. So let's take this first row, and we need to multiply that by the first column of B. And as I said before, just imagine flipping that first row of matrix A, essentially, by 90 degrees in clockwise direction. So we have 3 over 2, and we multiply that by a minus 5, 6. We have to add the corresponding components together. So this first entry is going to be 3 times minus 5, which is minus 15, plus 2 times 6, which is 12. So that is the first row, first column of our product. To get the first row, second column of our product, what we need to do is we need to multiply the first row again by the second column of B. So first row, second column is first row of A, second column of B. So we find this is 3 times 2, which is 6, plus 2 times minus 3, which is minus 6. Okay, then getting the first row, third column, again multiplying the first row of A, third column of B, we see that this is going to be 3 plus 0. Or the second row, first column of our product is going to be the second row of our first matrix times the first row of our second matrix. So here we have minus 5 plus 30. And then to get the other elements, we're going to do the same as we did in the row above. So just 1 times 2, 2 minus 15. And then the third column, second row, is going to be 1 times 1 plus 5 times 0. So it's just going to be 1 plus 0. Doing that then for the final row. Good. So if we just work that out, we get minus 3, 0, 3, 25, minus 13, 1, 34, minus 16, and minus 2. So this is our product. So it's really important to get used to how we multiply matrices. It's a little bit confusing at the start, but the more practice we do, the better we're able to kind of visualize these problems and work these out. So I really hope you enjoyed that first online maths video. We're going to be back with plenty more, so I hope to see you back again. In the meantime, check out some of our other videos from other great tutors in subjects such as economics, geography, biology, ESS, you name it. I hope you enjoyed this video, and I hope to see you next time.